Hello, in this lecture we'll find out the radius of a circle. In the drawing we have square ABCD and this circle, and this is line segment AP that is equals to 1 unit in its length. This is line segment QC that is equals to 4 units in its length. And our mission is to find out the area of this circle. In addition, we know that this is the point of tendency of tangent AB with this circle, and this is point Q, that is the point of tendency of tangent BC with this circle, and our mission is to find out the area of this circle. So first of all, we know that all the angles inside square ABCD are right angles. So those four angles, this is a right angle, this is also a right angle, this is a right angle, and finally this is also a right angle. We define the center of this circle, this point, as point O. We define the point of tendency of tangent AB with this circle. This point is point M. So here actually you can implement rule 1. So click quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn through its point of tendency. So in the drawing we have a circle, and we also, this is tangent AB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have the radius OM, the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So I can actually implement rule 1 in our drawing. So first of all, we join points O and Q together by a straight line. We define the radius of this circle as x. OQ is of course the radius of the circle, that is equal to x according to our definition. So here we have the radius OQ that is equal to x. The radius OQ is drawn to point Q. Again, the radius OQ that is equal to x. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together by a straight line. Point N is the point of tendency of tangent AB with this circle. ON is of course the radius of this circle that equals to x according to our definition. So again, here we can implement rule 1, because we have the radius ON that equals to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral M O QB, inside this quadrilateral, we have 1, 2, 3 right angles. The sum, again, inside quadrilateral M, O, Q, B, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral MOQB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral MOQB as a rectangle because it has 4 right angles. So quadrilateral MOQB is a rectangle according to rule 5. Again, quadrilateral MOQB is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MOQB, side MO must be equal to the opposite side QB. But MO is X, therefore QB must be also equal to X. Likewise, according to the same rule, in the same rectangle MOQB, side OQ must be equal to the opposite side MB. But OQ is X, therefore MB must be, the opposite side MB must be also equal to X. So we found out that quadrilateral MOQB is not a rectangle but a square because it has 4 right angles. Okay. So in the next step we know that ABCD is a square, and we also know that all the sides of a square are equal to each other. That is to say, side AB equals to side BC. In square ABCD, side AB must be equal to side BC. So I write it down. AB equals to BC. It is true in any square, and especially it is true in square ABCD. So AB equals to BC. According to equation 1, AB equals to BC. AB is AN plus MB. Again, AB in total equals to AN plus MB. So write it down. AB equals to AM plus MB. And it is equals to BC. BC equals to BQ plus QC. Again, BC equals to BQ plus QC. So AB equals to MB plus MB, and BC equals to BQ plus QC. So according to equation 1, AM plus MB equals to BQ plus QC. Again, AM plus MB equals to BQ plus QC. AM plus MB. MB is X. So we substitute MB by X, and it is equals to BQ. BQ is also X plus QC. It is given us the question that QC, the length of line segment QC is 3. So we substitute QC by 3. In total, we found out that according to equation 1, AM plus X equals to X plus 3. Here we subtract X from this equation, equation 1, and finally we get that according to this equation 1, AM equals to 3. AM equals to 3 units in its length. So this is line segment AM, it equals to 3 units in its length. In the next step, we will do a construction, that is to say, from this point B, we will go perpendicular on MO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and NO, this point is point N. So inside the small quadrangle APMN, inside this small quadrangle, inside the green quadrangle AMNP, we have 1, 2, 3 rectangles. This angle equals to 90 degrees because ABCD is a square, and this is one angle out of 4 angles of square ABCD. Therefore, it is a right angle. This angle equals to 90 degrees according to rule 1, and this angle equals to 90 degrees according to our construction. So in total, inside the green quadrangle MPMN, we have 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-picing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4-picing angle must be equal to 90 degrees in its size. So inside the small green quadrangle MP and M, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this rectangle, if not a square. So we relate to the green quadrangle MP and M as a rectangle because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So rectangle MP and M, side AP must be equal to the opposite side MN. But AP is 1, therefore MN, the opposite side MN, must be also equal to 1. Likewise, according to the same rule, in the same green rectangle AM and P, side AM must be equal to the opposite side PN. But AM is 3, therefore PN must be also equal to 3 units in its length. What is the length of the line segment NO? What is the length of NO, this line segment NO? From the drawing, it is very easy to see that NO in total equals to MO minus NO. Again, NO in total equals to MO minus MN. So NO in total equals to MO is the radius of the circle that is X, minus MN. We just right now found out that MN equals to 1. So in total, NO equals to X minus 1 unit in its length. So this is line segment NO that is equals to X minus 1 unit in its length. In the next step, we join points P and O together by a straight line. What is the definition of line segment PO? Line segment PO starts from the center of the circle, that is to say from point O, and ends at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of the circle, that is equal to X. In the next step, we will implement the Pythagoras theorem on the right triangle P and O. So we copy the right triangle P and O in a new page, and we will implement the Pythagoras theorem on this right triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. NO equals to X minus 1 unit in its length. Side PN equals to 3 units. And PO is the radius of the circle, is equal to X units in its length. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle P and O that are coming from the original drawing. According to the Pythagoras theorem, in this right triangle P and O, PO squared, that is the square of the hypotenuse, is equal to Pn squared plus NO squared. So I'll write it down. PO squared, that is the square of the hypotenuse, is equal to Pn squared plus NO squared. Okay, again, according to the Pythagoras theorem, in this right triangle P and O, PO squared equals to Pn squared plus NO squared. Again, PO squared equals to Pn squared plus NO squared. PO is x, therefore PO squared is x squared, and it is equals to Pn squared. Pn is 3, therefore Pn squared is 3 squared, that is 9, plus NO squared. NO is x minus 1, therefore NO squared is x minus 1 squared. So in total, according to the Pythagoras theorem, in this right triangle P and O, we actually found out that x squared equals to 9 plus x minus 1 squared. We'll open the brackets on this side of this equation, and we get that according to this equation, x squared equals to 9 plus x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So here we have x squared on both sides of the equation, so x squared will get cancelled. In this side of the equation we left with nothing, that is to say 0. The other side of the equation we have 9 plus 1, that is 10, minus 2x. So in total we found out that 0 equals to 10 minus 2x. Here we will add 2x to this equation, and we get that 2x equals to 10. 2x equals to 10. Here we divide this equation by 2, and finally we get that x equals to 10 over 2 is 5. So x, that is to say, the radius x of this circle is equal to 5 units in its length. The area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the area of our circle must be equal to pi x squared. X is 5, therefore x squared is 5 squared, that is 25. So pi is x squared is 25 pi. In terms of numbers, 25 pi is 78.54 square units. So we actually found out that the area that we are looking for, that is the area of the circle, is equal to either 25 pi square units, or in terms of numbers, the area of this circle is equal to 78.54 square units. So in the next step, I'll summarize the lecture. So in this lecture, we found out the area of this circle. So in the drawing, we have a circle and also square ABCD. Actually, square ABCD, side AD of square ABCD cuts the circle at point P, and side BC of square ABCD is tangent to the circle at point Q. In addition, we know that this is the small line segment AP, that is equals to 1 unit in its length. This is the small line segment QC, that is equals to 3 units in its length. And again, our mission is to find out the area of this circle. First of all, we know that all the 4 angles inside square ABCD are right angles. So those 4 angles are all right angles. And we defined the center of this circle. This point is point O. We define the radius of this circle as x. We join points O and N together by a straight line. ON is the radius of the circle that is equal to x. Why ON is the radius? Because line segment ON starts from the center of the circle, that is to say from point O, and ends at point N, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore ON is the radius of the circle that is equal to x. We join points O and Q together by a straight line. OQ is also the radius of the circle that is equal to x. Here we can implement rule 1. Why? Because of the fact that we have the radius OQ that is equal to x, the radius OQ is going to point Q, that is the point of tendency of tangent BC with this circle. And whenever your radius is going to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, according to the same rule, we join points O and M together by a straight line. OM is the radius of the circle that is equal to x. Again, we have the radius OM that is equal to x. The radius OM is going to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral MOQB we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral MOQB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be the rectangle if not a square. So we relate to quadrilateral MOQB as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle MOQB, side MO must be equal to the opposite side QB. But MO is x, therefore QB must be also equal to x. Likewise, according to the same rule, in the same rectangle MOQB, side OQ must be equal to the opposite side MB, but OQ is x, therefore MB must be also equal to x. So finally, we actually found out that quadrilateral MOQB is not a rectangle but a square. Why? Because of the fact that all 3 sides are equal to each other. Each side of this quadrilateral is equal to x, and therefore quadrilateral MOQB is a square. Okay? We know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC. In square ABCD, side AB equals to side BC. But AB in total equals to AM plus MB. AB equals to AM plus MB. Again, AB equals to AM plus MB. And it is equals to BC. BC equals to BQ plus QC. Again, BC in total equals to BQ plus QC. BC equals to BQ plus QC. So in total, we actually found out that according to equation 1, AM plus MB equals to BQ plus QC. AM is the missing side, so we leave it as it is, plus MB. We already found out that MB equals to x, that is the radius of the circle. So we substitute MB by x, and it is equals to BQ. BQ is also x, so we substitute BQ by x. Plus QC. It is given us a equation that QC equals to x, therefore we substitute QC, this equation 1 by, it is given us a equation that QC equals to 3, therefore we substitute QC in this equation 1 by 3. So in total, according to equation 1, we actually found out that AM plus x equals to x plus 3. Here we subtracted x from this equation 1, and finally found out that according to this equation 1, AM equals to 3. So we found out that this line segment AM equals to 3 units in its length. In the next step, we did the construction, that is to say from this point B, we drew perpendicular on MO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and MO, this point is point N. So inside the small green quadrilateral A, P, N, M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in size. So inside the small green quadrilateral A, P, and M, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a right angle and not a square. So we relate to quadrilateral A, P, and M as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle A, P, and M, side AP must be equal to the opposite side NM. But AP is 1, therefore NM must be also equal to 1. Likewise, according to the same rule, in the same green rectangle AP and M, side AM must be equal to the opposite side PN. But AM is 3, therefore PN is also 3. What is the length of this line segment NO? From the drawing it is very easy to see that NO equals to MO minus MN. Okay, again. ON equals to MO minus MN. So ON equals to OM is X, it is the radius of the circle that is X, minus MM. We just write down for now that NM equals to 1. So in total, ON equals to X minus 1 units in its length. In the next step, I copied the right triangle PNO in a new page and we implemented the Pythagoras theorem in this right triangle PNO. So here, this is the right triangle PNO that I copied from the original drawing according to the Pythagoras theorem. In any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this right triangle PNO is PO, so therefore the square of the hypotenuse is PO square, and PO square equals to PN square plus NO square. Again, PO square equals to PN square plus NO square. This right triangle PNO. PO is X, therefore PO square is X square, and it is equal to PN square. PN is 3, therefore PN square is 3 square, that is 9, plus NO square. NO is X minus 1, therefore NO square is X minus 1 square. So in total, according to the Pythagoras theorem, we actually found out that X square equals to 9 plus X minus 1 square. We open the brackets on this side of the equation and finally found out that according to this equation, X square equals to 9 plus X minus 1 square. X minus 1 square equals to X square plus 1 square, that is 1, minus 2 times X times 1, that is minus 2X. So in total, we actually found out that X square equals to 9 plus X square plus 1 minus 2X. We have X square on both sides of the equation, so X square will get cancelled, and we left only this side of the equation, we left with nothing, that is to say 0. On the other side of the equation, we have 9 plus 1, that is 10, minus 2x. So in total, we should find out that 0 equals to 10 minus 2x. Here we added 2x to this equation, and finally found out that 2x equals to 10. Here we divided this equation by 2. And finally found out X, that is the radius of this circle, is equal to 5 units in its length. X equals to 5. The radius of our mission is to find out the area of this circle. The area of any circle is pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x. The radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 5, therefore x squared is 5 squared, that is 25. So pi x squared is 25 pi. So in total, we should find out the area that we are looking for in this question, that is the area of the circle, it is equal to either 25 pi, or in terms of numbers, it is equal to 78.54 square units. Okay, thank you very much.